What if there was just one simple rule that could explain everything? I mean, from a clock slowing down on a spaceship to light itself bending around the sun. Well, today, we're going to dive into a bold new proposal in physics called relator theory, which suggests exactly that. Let's see what it's all about.
And that puzzle, boy, is it the central challenge of modern science. See, we have two theories that are just unbelievably successful at describing our universe. But when you try to get them to work together, they fundamentally, even violently, disagree. It's like having two perfect instruction manuals for a machine, but they describe completely different parts that just don't fit.
So let's just quickly lay out the two sides of this epic puzzle. On one hand, you have the world of the absolutely immense, and on the other, the world of the infinitesimally small.
Okay, so on one side, you've got general relativity. That's Einstein's masterpiece. It gives us this beautiful picture of gravity as this graceful curvature of a smooth, continuous fabric of spacetime. The thing that governs planets, stars, and whole galaxies. Then on the other side, you have quantum mechanics, which describes the totally bizarre, probabilistic world of tiny particles, where everything is made of these discrete little packets or quanta. The problem? Well, when you try to use both theories to describe something like a black hole, which is both incredibly massive and incredibly small, the equations they completely break down. They give you nonsense.
And this is where relative theory comes in. Instead of trying to somehow stitch space, time, and quantum fields together, it proposes a completely new foundation, a foundation built on a single universal principle. You can think of it as a kind of cosmic speed budget that every single particle in the universe has to obey. No exceptions.
So this is it. This is the one and only new rule the theory introduces, RW equals C. Let's break that down real quick. Imagine every particle isn't just a point, but it has this tiny, hidden internal clock that's always spinning. R is basically the size or radius of that spin, and omega, that's omega, is how fast it's spinning. And what the theory says is that for every single particle in the universe, if you multiply that internal size and its internal speed, you always get the speed of light, c. It's an unbreakable universal law.
So how can we even picture this? Well, this slide actually helps us visualize the two arenas of existence in this theory. We live and move around in our familiar three-dimensional world, right? The paper calls that R3 space. But the theory proposes that every particle also exists in this other hidden space, a complex internal space that it calls C space. Now, complex here is just a mathematical term, but you can really just think of it as a hidden dimension where that fundamental spinning, that internal clock, is actually taking place.
Okay, so here's where that speed budget analogy really starts to click. Think about it like this. A particle that's just sitting still in our 3D world is actually using its entire speed budget to spin internally in that hidden C space. And that constant internal ticking is what we actually perceive as its mass. But what happens when that particle starts moving through our world? Well, it has to borrow from its internal spinning speed to pay for its external motion. And because that total budget has to always equal c, its internal clock must slow down. And right there, from that one simple idea, the theory directly derives one of Einstein's most famous predictions, time dilation. Deriving time dilation from just one simple rule? I mean, that's impressive. But the real test, the acid test for any new theory of gravity, is whether it can match Einstein's most famous predictions.
And that really is the big question, isn't it? Einstein explained gravity as massive objects literally bending the fabric of spacetime. So how on earth can a theory with no curved spacetime possibly account for something like the sun bending the path of a beam of light?
The answer is pretty radical. Relator theory says gravity doesn't warp space at all. Instead, it suggests that a massive object like the sun actually influences how a nearby particle is allowed to use its speed budget. It basically forces a photon of light, for example, to reallocate its energy, shifting some from its internal spin to its external motion. And that's what causes its path to bend.
And here's the absolutely astonishing result. When you work through the math of this speed budget reallocation, the theory spits out a number, an angle, for how much light should bend as it passes the sun. And that angle is precisely the same value that Einstein's theory of general relativity predicts, a value that, as we know, has been confirmed by experiments for over a century. It's a completely different path that leads to the exact same destination.
Now, let's do a quick numbers check against one of the most precise tests of gravity ever done. Back in 2002, the Cassini spacecraft measured the time delay of a radio signal as it passed by the sun. This is a super sensitive test of gravity. And guess what? The prediction from related theory matches the actual Cassini measurement to within about 10 parts per million. That level of agreement is just stunning, and it gives this brand new idea some really strong empirical footing.
Okay, but it is absolutely crucial to be clear-headed here and separate what this paper rigorously demonstrates from what it's just suggesting for the future. We really have to avoid the hype and just stick to the facts. And the authors are actually very careful about this. The column on the left shows what they can derive directly from their one principle, at least under weak gravity conditions. Things like time dilation, the bending of light, and even some properties of particle spin. But the column on the right? That shows the ideas they're proposing for future research. How this theory might explain quantum entanglement or the crazy physics inside a black hole. Those are still very much open questions. So all of this brings us to a really profound, almost philosophical conclusion. Because if this theory holds up, it could genuinely reshape our most fundamental understanding of what reality even is.
And this, right here, is the key takeaway. The paper is suggesting that space-time curvature, the central pillar of Einstein's theory for over 100 years, might not be fundamental at all. It might just be an effective description, kind of like a mathematical shadow that's being cast by a deeper reality, which is this universal quantum rule, R omega equals C.
So we're left with some pretty deep questions to ponder. Is the very stage of our universe, space-time itself, truly fundamental? Or is it just an emergent property of some simpler quantum rule? Could it really be that the vast, mind-boggling complexity of the cosmos all boils down to a single, elegant constraint? And if that's true, well, what other cherished principles of physics might just turn out to be beautiful illusions, waiting for us to uncover the simpler truth that's hiding underneath?